the energy method and continue. So last time we deal with the systems. So for kinetic energy, and for single degree of freedom is mx squared, and for potential energy we have say for MEQ, for KEQ, and that is x squared. Okay, so the total energy equal to K plus U. So last time we do the derivative of the total energy. So that's why we're taking the derivative on the terms here. Then we can find is equal to this. Okay, so with this result in mind, then here we can discuss for undamped vibrations, and our systems are described by this. Okay, so basically it's MEQ, KEQ. Okay, so therefore from plugging to here, then we have is d dt, the total energy equal to 0. So that is a conservation of the total energy for undamped vibration systems here. And today we're going to continue to have more exercise from here. And for the other scenario for damped vibrations, and we have MEQ x double dot plus CX dot plus KEQ x equal to 0. Let me say this is CEQ as well. So from here you can see basically MEQ plus double dot plus KEQ x will be equal to minus C EQ x dot. Okay, so therefore plug into here you can see ddt of the total energy. If you plug in these terms into here, then you can see that equal to CEQ multiplied x dot square. Okay, and this one is always positive square terms, and C is a damping constant, and that is the positive term. So basically this one will be always less than negative until it's everything dissipated until x dot become to 0, it will stop. Okay, so that means for damped vibration systems, the total energy is decreasing. Okay, so later on we will have more discussion. So let us save this to the sections of damped vibration probably on Wednesday. Okay, so today we focus on this, and we see how can we utilize this principle here. So for undamped vibrations, and again we're dealing with MEQ double dot plus KEQ x equal to 0, and we have a conservation of the energy. Okay, so that is the first one. And this implies the d dt over t equal to 0, or we want to say is d dt kinetic energy plus potential energies equal to 0. Okay, so we continue to apply this one to solve for some problems. Then the second one, the second features of this is conservation of the total energy equal to constant. So that means we, in particular for the vibration systems, we know that the vibration is such that when the system going to the maximum deformation, then at that moment velocity equal to 0. Listen this again carefully. For vibrations, assuming we take for a special, without considering the phase angle. Phase angle doesn't affect the shape of the vibrations. Okay. You know that this is the time. This is our displacement. This is the maximum displacement. That means representing the maximum displacement, the maximum deformation of the spring, at which the point, the slope equal to 0. So that means corresponding to the maximum deformation, that is the maximum potential energy, upon which the kinetic energy equal to 0. Again, at another point, we know that the slope is maximum, which means the velocity is maximum when the x equal to 0, no deformations. So that means because the total energy is constant, and also the total energy equal to the kinetic energy plus potential energy. And for this case, we have the for scenario, say for case A, let me say this is the point A, this is point B. At A there, we have the maximum kinetic energy. At point A, we have a maximum potential energy. And at that moment, our kinetic energy equal to 0, right? At point B, we have a maximum velocity. That means the maximum kinetic energy. At that moment, the x equal to 0, so that means the potential energy equal to 0. So this quantity equal to this quantity because of the conservations. So that means from here, we know that the maximum potential energy equal to the maximum kinetic energy. Okay, so that is the second features we can utilize for solving the thing. So now we can see how we can do it. So let me utilize, let me call this is a feature. We can exercise this first, okay? So we let xt, okay, we know that for damped vibrations, we have the generic term is the magnitude times cosine, and known the certain omega t minus v, okay? So we know that is a template for the general solutions. And capital X here representing its amplitude vibrations, omega nt representing the undamped natural frequencies. And I'm going to show how to use this property to solve for omega nt without deriving the equation of motion. Okay, again, right now here I'm going to do it is to show you the applications of the two features here. Okay, the first one you can see. So from here you can see x dot. Let me take the derivative, and that is capital X omega n times minus sine omega nt minus v. Okay, so now we have this one. And so from here we simply plug in the kinetic energy maximum, basically is equal to m times x dot maximum, right? So what is this value? This value, if you look at this derivative here, basically the derivation here, that is m. The maximum value of the velocity, you're looking at here, is when psi equal to, this value equal to 1. So basically that is capital X omega n squared, right? You good? Okay, and now we look at the maximum potential energy, and that is, sorry, so let me just use the m equal k, okay? So the kinetic energy is x squared. And what is the maximum? The maximum value is happened at the maximum displacement. So there's an m cubed, so 1 KEQ. So what is the maximum x? The maximum x simply is capital X, right? Because you can see the maximum value. So from here I can put a note. Therefore, x maximum equal to x, and x dot maximum equal to x omega n. Let me put a note here. That'll be clear. Okay. So by using the maximum energy, kinetic energy equal to the maximum potential energy, then we have is 1/2 MEQ capital X omega n squared equal to 1/2 KEQ and capital square. So from here we can compare, cancel the common terms from the both sides. You can see omega n basically equal to KEQ and divided by NEQ. So this one leading to the same expressions of the natural frequencies without going to the equation of motion. And we can look at one example here. So we consider again using a pulley, and this is spring constant K, and using a pulley to support a mass, and this is M. So this is a wire going around the pulley, and we define our degree of freedom as xt like this. Okay, so for this case, we want to apply this method. I want to apply this method to calculate the natural frequencies. And we have done this one before, so you can compare. And for this one, you can see the first one we formulate the maximum kinetic energy, and that is happened on the mass. And here we only have a mass block is here, so 1 times m times the degree of freedoms, the velocity of that one, and that happened is x dot. And here we're looking for is a maximum, okay, squared. And by doing so, we have to assume the vibrations. So that means let me take the, we assume the magnitude is capital X times cosine and omega nt minus phi. Let xt equal to this. And here I'm using the word let. That means we assume everyone has understood and why the solution is like this pattern. Okay. And that means this word, behind this word, that included couple hours of the lectures and about the undamped vibrations, about the how to formulate and how to solve for the solution. And now we know that solution is in these patterns. Okay, you must have that preparations, otherwise just take it. And then here we take the derivative, and that is similar to there, omega n x and minus sine omega nt minus phi. Okay, with that one, so here the maximum equal to x, and x dot maximum equal to x omega n. So we plug in here, so it's 1/2 m times capital X squared. Okay. And also we formulate the potential energy. Potential energy from here is K times, again, that term is a certain maximum square, and that term representing is the deformation of the spring, right? Deformation of the spring, if you remember for this case, the twice amount on the mass block movement equal to half the one amount of that spring. So here the spring deformation is x over 2. Okay? why have this? Again, we have certain examples last week, but also you can refer to your statics about why the spring deformed by x over 2, and that can be related from your statics. You can go for that one, or simply look at our lectures last week. Okay. Sorry, here I forgot. Seems I forgot one term, omega n squared, right? Because I need to plug in there, so I forgot. So here, okay. So here for this example is 1 times 4k, and the maximum we plug in is x squared. Okay. So therefore, by plugging here, then by k max equal to u max, then we have is 1/2 mx squared omega n squared equal to 1/2 k over 4x squared. So therefore, you can cancel 1/2 here. We can cancel capital X squared. So leaving to omega n squared equal to k over 4n. So therefore, omega n equal to k over 4n. Okay. So from this exercise, we have not derived any equation of motions, but we can directly calculate the vector frequencies. Then we can, another example related to exercise in this one, okay, and so we can try is so right now I'm going to exercise is this one. Basically, this approach and this approach, they are equivalent. They're basically based upon the conservation of the energy. So we can use this one. And so that kind of the water in a U-tube. Okay, so initially the water built up and in static equilibrium into this. Okay, and the whole length of the water in the tube is, let me call L. And say, let me call the water, this tube has the cross-sectional area A. Okay. That is uniform. So right now we are going to apply certain pressure to push the water and to cause certain vibrations. And what we set up is this. We on this end, at this end we simply press down by amount of x, and the water, due to continuity, is going to raise at the other end by the same amount x. So right now our setup is like this. So we're going to apply certain kind of push, and then we release the push, have the water to free vibrate in this tube. And assuming there are no frictions, okay, so that means here we assume is undamped vibrations. So that means the undamped vibrations. So we want to calculate to find omega n is undamped natural frequencies here. So our solutions, and we can do is like this. I'm going to apply using the principle, the derivative of the total energy is 0. Okay, so we simply focus on to formulate the kinetic energy and potential energy of these systems. For system to vibrate, the total kinetic energy basically is proportional to its mass. Assuming it has the rho is the density per length, so multiply with L equal to the whole mass times, sorry, if really we want to do this one, so let me do this again. So the length multiplied with cross-sectional area of the tube equal to the volume of the liquid. And let me assume the rho density, the liquid have the density of rho. So rho times LA, that means the whole mass of the liquid. Okay. And now we designate the coefficient, so that is x dot squared. Now we on the potential energies. Potential energy, this is a little bit tricky, so that's the reason why I want to explain in details. And so if we compare the liquid in these portions under this line basically they the same. So the only thing that's going to affect to change the potential energy is due to the liquid inside these portions and also inside this portion. Right? Okay, so we simply focus on the change of the potential energy due to the change of in that kind of the right side. So for this portion, you can see the change in energy. The potential energy is mgh in general, mass, gravity, and change in the height, mg delta h. That means the change in the potential energy, right? Okay, so now for this portion, it has rho density times A times X, that is the total volume of this portion. And it change by going down. Okay, so going down, let me say going down is negative X over 2. Okay, and here again, the liquid in this portion is depleted. That means its mass is reduced. So here I would say this is also minus here. Okay? Compared to this portion here, in that portion we have the volume equal to how much? The X times A, that is the volume, times rho is the mass, and mass times G, and times the change in height equality is X over 2. Good? This is increasing due to the existing mass. This is the change in the potential energy due to depletion of the mass. We plus together. The two things, do this one carefully, is rho A X squared. Good? Okay. Yes?
I think you said this a couple times, but I missed it. Why is it X over 2?
Yes. So for this one, this is because this is a uniform mass and uniform distributed. So here is equivalent change in the potential simply is we take the center of the mass there and this is X over 2. we simply take the whole mass and multiply with g, multiply with the equivalent height. Yeah, okay, so that's taken to that one. So once we have this one done, then we simply take it as d dt of plugging here, and 1/2 and rho LA x dot square plus 1/2 rho. Sorry, here you see, yeah, I think that's okay. Plus rho 8x squared equal to 0, right? Okay, so now rho gh. I think you see I'm going to be missing quite a bit terms here. Here I forgot the term times g. Okay, so here I forgot the terms g here. So here I need to add another term here. So from here we can, before we're doing something, we can cancel the common terms rho. We can cancel a, and we can cancel, that's it. So now we do need more calculation here. So let me finish. So that is the d dt 1/2 L x dot square plus g x square equal to 0. Okay. The first term is equal to x double dot times x dot. Again, you carefully do the chain rule to the first term. And then we take the derivative on the second term, that is 2g times x dot. Again, you take the chain rule on the second term here. We have this. So now we become x double dot plus 2g x. And let me, because they have a common x dot term, let me take the x dot term to the outside here. Okay? So therefore, we have this one, x Lx double dot plus 2g x equal to 0. So from here, this actually is our equation of motions. And equation of motion, then here you can right away to write it down, the omega natural frequencies equal to 2g divided by L, and take the square root. Okay? So using the second approach, basically this is the, we're going to do this again in the multiple degree of freedom probably in November. Okay? And this is the energy-based formulations. And this one, this is more general than this one. This one actually can give us the equation of motions. Okay? So keep both things. I think that is the demonstration of the whole things here. Any questions about the two examples?
Where do you get